So in this video we're going to talk about combinations of functions. There's two main things that we'll be talking about in this. The first one is the arithmetic combination of functions, which quite frankly is pretty straightforward. So what we have here is we'll let f and g I can't write right now for some reason. Let f at x and g at x be functions with overlapping domains. And what it means by to be overlapping domains is that there is something to actually be done here with the overlapping domains. Because if you have things that aren't defined, and you're trying to add something to an undefined number or subtract something, who knows what's going on then. So that's just saying that essentially they have domains that are similar, or at least parts of them that we could consider to be similar. Like we might not be able to consider the full domain, but at least the most of the domain. Alright, so these are pretty straightforward. You can add functions, and the notation for adding two functions is f plus g in parentheses at x, but we literally just, as you might guess, add the two functions together. Well, then there's the difference, which is just f minus g at x, and as you might guess, what are we going to do? We're literally going to subtract them. Alright, you probably get where this is going. We can multiply to the product f times g at x, and what are we going to do? We're literally going to multiply the two functions. And then the last one, of course, is the quotient. And as you guess, we're going to just divide my functions. But there is one additional stipulation we need to put here. This is just equal to f at x over g at x, provided g at x does not equal 0. And of course, if you think about it for a second, the reason I have to add that in is because I can't divide by 0. So essentially, yeah, the quotient is just f divided by g, except when g is not equal to 0, except only for g not being equal to 0. What happens when g is 0? Well, it's just undefined. So there's not really much that's going on, it just is undefined. Alright, so let's look at this here, and a couple examples here. So if we have here f at x equals x squared plus x, and then g at x is equal to x minus 1. Let's go ahead and find f plus g at x, f minus g at x, f minus there, let's try that again, f minus g at x, f times g at x, and then we'll actually do two here, f divided by g at x and g divided by f at x. So we're going to do all three of these here. Alright, so let's go ahead and a couple of these, actually I think I can probably all do them all on the line here. So f plus g would just simply be x squared plus x minus 1, and then you simply combine like terms, and so this would be x squared plus 2x minus 1. Pretty straightforward. F minus g, same idea. Don't know what just happened there. Just a second. Alright, sorry about that. There's different tabs on my notepad here, and my hand accidentally bumped one of the other tabs on the touch screen. So that's what happened. So back to this here. So we had f plus g, which again was just simply combining like terms. Now if we do f minus g, it's going to be the same idea, except it's x squared plus x minus x minus 1. And then making sure to distribute that negative, you would get x squared plus 1, because you'd have x minus x, and then a negative negative 1, which is positive 1. And then f times g would just simply be x squared times x minus 1. Then we'd just FOIL this out, and we'd get x cubed plus x squared minus x squared minus x, and then we simply combine like terms, and we'd wind up with x cubed minus x. Now f divided by g, well, there's really not a lot we're going to be able to do with this. This would just be x squared plus x divided by x minus 1. But the one thing when you divide, you should always restate what your domain is here, and the domain is all of r except, well, my denominator now, I can't be 1. And then if we do the same thing here with g divided by f, this would be x minus 1 divided by x squared plus x. And this would be the domain is r except, and I'm just going to do this in my head, but if you want to see how I know it's except x equals 0 or negative 1, remember what we do is you set your denominator equal to 0, and in this case you could just factor an x out and you would get x equals 0 and negative 1. So pretty straightforward. And in fact, that's all I'm going to spend time about talking with adding, subtracting, multiplying, and dividing functions, because it's pretty straightforward. Now, the one that I'm going to spend a little bit more time on here is composition of functions. Composition of functions is not difficult to evaluate, but knowing what the domain is and knowing what the range is especially is a little bit more challenging. Now we're going to focus on what the domain of a composite function is. Now let's just talk about what we have here. So this is a definition here, and I'm also going to kind of draw a picture here. And so the definition here is the composition of the function f with the function g is, and then this is notation here, f little circle g, that's for composition. Now this is actually a notation that is actually sometimes used and sometimes not used, but it is it's used enough that it's important that we notice the fact that this is f composed with g, and then this is equal to, the way we do this is we say it's f evaluated at g at x. Now we'll get into evaluating these with some examples here, but let's talk about what the domain is. The domain of f composed with g is the set of all x in the domain of G such that G at x is in the domain of f. Now that sounds a little confusing, but I am going to kind of draw a little figure here to illustrate what a composite function does, and then we will go ahead and look at some examples here and also look at the domains. Alright, so as the picture here, the idea here is, remember, we had these function boxes that I had kind of drawn when we first started talking about functions. And now, the one that's going to do here, just by the definition, the first thing we're going to do here, order of operations says we do what's inside the parentheses. So this is going to be the function box G. And so remember, with these function boxes that we have here, we have an input, and this input here, of course, is just x, and then the output of this function box would be G at x. Now, if this was just G, that would be fine, but then what do? We have this is going into another function box, and the other function box it's going into is a function box and we'll call it f because that's the other function. But what's going into that? What's going into this, the input is G at x because that's what's going into the box, and then out of the box is coming f at G at x, or the composition of f with G. Now, this is where the domain gets a little interesting when you're doing these problems. So again, we have to say first off, what's the domain of G? Because those are the only allowable inputs. So we can't have, if you can't plug it into G, because that's the first thing we have to do, then we can't, use that as part of our domain. So we have to see, okay, well, what can I plug into G? And then once I've determined what I can plug into G, I get my outputs G at x. But now G at x is the inputs into the function f, and so I have to determine, okay, well, what are the outputs of this that are allowed in as far as inputs? And an example here would be, for instance, an easy example would be, for instance, if we had square root of x in here as the second function box, and then we had x minus 1 as the first one. And the reason this is an easy one, and we'll go in more detail when we go through some examples here, is that when we have the inputs here, the domain for this first one is all real numbers. You can plug in any real number here and it'll be fine. But the domain for square root of x, remember, is that x has to be greater than or equal to 0. So I have to say, well, the outputs are the only ones that have x greater than or equal to 0, so I have to figure out, okay, well, when is this output? So in other words, when is x minus 1 going to be greater than or equal to 0? And of course, that's x is greater than or equal to 1. Now, there are easier ways to do this. Sometimes the easier ways to do this is just, seeing what your domain is of the final function. And what do I mean by that? Well, you'll see when we get to some examples here. So let's look at a couple examples. Let's start with some easy ones where the domain is straightforward and there's nothing that we have to concern ourselves about. So f at x is equal to 2x plus 5, and then g at x is equal to 4x squared plus 1. And we're going to find both f composed with g at x and g composed with f at x, because you can do either one, but you will, for the most part, get a different answer. Okay, so let's look at this here. So let's first do f composed with g at x. Now I like to write down the computational version of this, which is f at g at x, because then we just do substitution. And what do I mean by substitution? Well, what is g at x? G at x is 4x squared plus 1. So let's substitute that in. F at 4x squared plus 1. Now this is still just a function evaluation. We've done this before. Now what we do is we substitute this in for x in the function f. And then we'll simplify and be done. This would be then 2 times 4x squared plus 1 plus 5. And so then we just multiply this out, simplify it, to get our final answer, which would be 8x squared plus 2 plus 5, which of course would simplify to 8x squared plus 7. Now we can do g composed with f at x, which this would be g at f at x. So the difference here is we're substituting in f first, so this would be g at, well, f at x was 2x plus 5, and then I'm going to substitute that in for x in my function g. So this would be 4 times 2x plus 5 quantity squared plus 1, which, evaluating that, would be 4. Multiplying this out, we get 4x squared plus 20x plus 25 plus 1. Again, simplifying this out, 16x squared plus 80x plus 100 plus 1, which finally simplifies to 16x squared plus 80x plus 101. Now you can see we don't get the same thing, so in general you won't get the same thing. There are special circumstances where you'll get the same answer for g composed with f and f composed with g. One of those special examples we'll be looking at in the next next video when we talk about inverse functions. Alright, but let's do one other example here that actually has us also have to deal with the domain. So let's look at f at x being x squared minus 9 and g at x being the square root of 9 minus x squared. Okay, so then let's look at f composed with g at x, which would be f at g at x, which is f at the square root of 9 minus x squared, which is equal to the square root of 9 minus x squared, quantity squared, minus 9. Okay, so we square that, and we get 9 minus x squared minus 9, which is just equal to negative x squared. Now, to finish this off and to finish this video off here, what is the domain of f composed with g at x? Now, the temptation might be to look at this and just say, oh wait, the domain is all real numbers, because you can plug any number into x squared. But that's not what you have to do. You first have to look at what is the domain of g. Well, what do we have here? This is a square root, and so 9 minus x squared has to be greater than or equal to 0. Now, we've solved these kinds of inequalities before. 9 has to be greater than or equal to x squared. Actually, I'll do it by the factoring method. I like that better. So we'd have 3 minus x times 3 plus x has to be greater than or equal to 0. And so if we look at our number line here, and we have -3 and then 3. Now I'm going to skip some of the computations. If we go through and plug in some values, we'll see that the intervals that are valid are from -3 to 3. So the domain of g at x is from -3 less than or equal to x less than or equal to 3. Now, what's the domain of my f? The domain of f is all real numbers. So I don't have to worry about what the output of g is, because g at x is going to be the input to f. But since f can take any real numbers, I don't have to worry about what the outputs are. But that means that the domain of f composed with g at x is -3 to 3. So these can be a little tricky, but again, just when you practice on them, you'll, I think, start to get the hang of them.